Good afternoon, doctor. Today our group is going to explain about Franklin Bell experiment. Before we move on to the Franklin Bell experiment, let us understand about what is Franklin Bell. Franklin Bell is an early experiment conducted by Benjamin Franklin to demonstrate the principle of electricity. In this setup, a central metal ball is flanked by two metal bells, each connected to opposite charges of an electrostatic machine. A metal clapper suspended between the bell would be attracted alternately to the positively and negatively charged bell, ringing as it moved between them. This experiment was significant in illustrating the behavior of electric charges and the concept of electrical attraction and repulsion, which is known as electrostatic charge. From that, we can even relate it with Coulomb's law and Gauss' law. To conduct the Franklin Bell experiment, we need to prepare the material as such, which is our aluminum can, a pencil, a thread, and plastic wrap. Next, let us watch about the experiment demonstration conducted by our groupmate. From the previous video, we can see that when we put a plastic wrap closer to the pull tab will swing back and forth and hit the can continuously. As a result, the bell sound is produced. Based on the observation, we found that the result can be explained by electrostatic force and Coulomb's law. This is because when the plastic wrap is put closer to the pull tab, it is previously rubbed using the cloth made by cotton. The electrons are moved from the cotton to the surface of the plastic wrap. The plastic wrap will become negatively charged, and this phenomenon is called electrostatic charge. When the negatively charged plastic wrap is brought closer to the pull tab, the excess electron on the surface of the plastic wrap will repel the electron in the pull tab due to the principle of electrostatic force outlined by Coulomb's law. Coulomb's law states that the force between two charged objects is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. As a result, the electrons in the pull tab will experience a force of repulsion from the electron on the plastic wrap. This repulsive force causes the electron in the pull tab to move away from the plastic wrap. Since the pull tab is suspended by a thread and it is free to move, the movement of the electrons will create an imbalance of charge within the pull tab, leading to one side of the pull tab become positively charged while the other side become negatively charged. This redistribution of charge will create an electric field around the pull tab, and this electric field we can derive it by using our Coulomb's law and Gauss' law and create a formula to calculate it. And this formula we will explain in our next slide. The electrostatic force between the charged plastic wrap and the charged pull tab will cause the pull tab to swing toward the plastic wrap. As the pull tab moves closer to the plastic wrap, the electrostatic force decreases due to the increasing distance between the two objects. Conversely, as the pull tab moves away from the plastic wrap, the electrostatic force will increase. This back and forth motion of the pull tab will continue, resulting in a continuous swinging motion and producing the sound of the bell hitting the can. And next slide, we are going to see the electric field intensity formula by using our Coulomb's law and Gauss' law. From the Coulomb's law, we can see that the electric field intensity is equal to the force divided by the charge. And from that, we can derive our formula, our electric field intensity, which is equal to Q divided by 4 pi epsilon naught R square, which the r is the unit vector direction. There's another method to calculate our electric field intensity, which is using the Gauss law. Gauss law is a method which is more simpler than Coulomb's law, and the formula is showing as such, which is the integration of d dot ds is equal to the q enclosed. Gauss law is defined as the integration of the electric flux density d over a closed Gaussian surface S is equal to the charge enclosed the surface. However, there's some restriction to using the Gauss law, which is it requires the infinite line charge, infinite surface charge, source as point charge, and the last one is a symmetrical charge distribution. Hence, we can conclude that although the Coulomb's law is more complex than our Gauss law, but it can be applied for all the cases, while Coulomb's law can't be applied for all the cases. As a conclusion, the Franklin Bell experiment demonstrates how the principle of the electrostatic force governed by Coulomb's law and Gauss law, which can cause the charged object to interact and produce the observable effect, such as the swinging motion of the pull tab and the sound produced when it strikes the can. This experiment illustrates the fundamental concept in electrostatic and electromagnetism, providing the insight into the behavior of charged objects in electric field.
And lastly, we are going to discuss some examples of the application of Coulomb's law. The first one is electronic. Coulomb's law is fundamental in designing electronic components like capacitors and electrostatic sensor. It helps in calculating the force between charge, which is crucial for understanding how this device store and sense electrical energy. Second, printing technology. In digital printing technologies like laser printers and photocopiers, Coulomb's law is used to manage the attraction of toner particles to charge drum units. This ensures precise image and text transfer onto paper.